As rovers ventured farther from their entry points, they uncovered an environment more intricate than any had predicted. The subglacial lakes were not simple pools, but dynamic, interconnected systems shaped by gradients of heat, pressure, and mineral flux. The lake floors resembled alien landscapes. Sediment layers formed rippling patterns, shaped by slow-moving underwater currents created by geothermal heat rising from the bedrock. Fine silt, carried from ancient rock layers, drifted in perpetual suspension, forming a thin atmospheric like haze beneath the ice ceiling. Rovers navigating through this haze recorded shimmering halos of reflective particles stirred by thermal upwellings. These currents were central to the functioning of the ecosystem. They transported nutrients released from bedrock erosion, distributing them across broad surfaces. In zones where the current slowed, the filament organisms congregated, forming mats that waved gently like deep-sea meadows. Where currents accelerated, organisms stretched into elongated strands, as if optimizing their exposure to the mineral-rich flow. The ice ceiling above was not uniform. Some regions were smooth, compressed by centuries of gradual accumulation. Others contained channels where meltwater carved narrow rivers through the underside of the ice, carrying dissolved gases and trace minerals. These channels hosted unique biological activity. Rovers detected dense concentrations of gel, like webs, attached to sealing ridge structures that pulsed faintly in sync with pressure variations from the overlying ice sheet. Further exploration revealed subglacial caverns, vast hollows formed by geothermal heating with roofs tens of meters high. These caverns contained calm water isolated from the main lake circulation. Here, the organisms formed intricate formations, delicate towers of filament bundles rising from the sediment like mineral spires, interconnected by shimmering membranes. These structures resembled biological cities or reefs, albeit without individual creatures. They were manifestations of collective organization, organic architecture sculpted by chemical and mechanical gradients. In some caverns, rovers found pools of dense brine trapped for thousands of years. These brines hosted different organisms, smaller and denser, adapted to high salinity. They glowed faintly under certain wavelengths, producing bioluminescent pulses that traveled through the brine like signals. The pulses coordinated the shifting pattern of microbial films, directing the flow of chemical energy across the brine pool. Perhaps the most astonishing discovery occurred in a tectonically active region beneath a mountainous section of the continent. Here, the lakebed was dotted with warm seeps vents, where mineral-rich water emerged from deep within the crust. These vents produced chemical gradients far more dynamic than their surroundings, and rovers recorded massive filamentary formations concentrated around them. These formations behaved differently from the mat organisms observed elsewhere. They expanded rapidly on the scale of hours rather than days, adjusting their architecture in direct response to mineral surges. Their electrical oscillations intensified, creating coordinated waves across kilometers of interconnected networks. It was the closest analog to large-scale biological activity ever observed in the subglacial world. Yet, despite this complexity, predation, competition, and hierarchic engines of surface ecosystems were largely absent. Energy flowed through gradients rather than through consumption. Organisms cooperated by default because their structures were physically interconnected, forming networks that resembled distributed intelligences rather than discrete species. The rover's maps revealed an ecosystem based not on scarcity, but on stability. It was a world shaped by slow rhythms and ancient processes, where life adapted not to sudden change but to geological timescales. In this realm, the ice above acted as both shield and dictator, defining the pressure, temperature, and chemistry that gave rise to a unique biosphere. Antarctica's subglacial world was not a frozen void. It was a shadow ocean with its own landscapes, currents, architectures, and dynamic patterns, an entire hidden Earth thriving beneath the frozen shield. The discoveries beneath Antarctica challenged not only biological theory, but also humanity's understanding of what made a planet habitable. The subglacial ecosystem demonstrated that life did not require sunlight, oxygen, or moderate temperatures. It needed only a stable supply of energy, whether chemical, mechanical, or geothermal, and enough time to adapt to extreme constraints. This revelation broadened the concept of habitability in profound ways. Moons like Europa and Enceladus, long suspected of harboring subsurface oceans now, seemed even more plausible as hosts of life. The Antarctic organisms provided a model for how biology could develop under ice sheets tens or hundreds of kilometers thick, isolated from the surface for geological ages. Furthermore, the unique biological structures found beneath the ice implied that heredity, metabolism, and growth could arise through pathways entirely independent of DNA and cellular architecture. Life could emerge from distributed networks, mineral scaffolds, or pressure-stabilized polymers. It could encode information spatially rather than sequentially, using rhythmic patterns instead of genes. These possibilities demanded a re-evaluation of astrobiological strategies. Instead of searching for familiar biomarker oxygen, chlorophyll, or complex organic molecule, scientists began exploring signatures associated with patterned electrical oscillations, isotopic anomalies, and dynamic fluid structures. Antarctica's hidden organisms became prototypes for recognizing unfamiliar life in the universe. On Earth, the subglacial biosphere also prompted new environmental questions. If such life had existed for millions of years, what role had it played in the planet's evolution? Its slow but persistent interactions with bedrock and meltwater could have influenced global geochemical cycles, contributing trace elements to the ocean and modulating the chemistry of deep crustal fluids. Though operating on vast timescales, this shadow biosphere might have subtly shaped Earth's surface environment without ever being detected. The possibility of contamination became a pressing ethical issue. Human activity, even carefully sterilized instruments, risked introducing foreign microbes into these delicate ecosystems. Such contamination could disrupt networks that had stabilized over millennia. New protocols demanded stricter barriers, sealed boreholes, and non-invasive observation techniques to protect the hidden world. Yet the most profound impact was philosophical. Life beneath the ice forced humanity to reconsider the definition of life itself. It demonstrated that biology was not limited to cells, genes, and photosynthesis, but could emerge wherever matter and energy arranged themselves into self-maintaining patterns, capable of adapting and responding to their environment. The organisms beneath Antarctica were not intelligence in the conventional sense, but they represented a form of complexity bordering on cognition. Their electrical pulses encoded environmental information. Their networks optimized energy flow. Their structures reconfigured in response to long-term patterns. They were alien yet terrestrial, familiar yet fundamentally foreign. In the end, the Rovers' discoveries under Antarctica's frozen shield did more than reveal a hidden ecosystem. They expanded the boundaries of the possible, showing that Earth still held vast domains unexplored, and that life, wherever it emerged, would always find ways to adapt, persist, and evolve under even the most extreme conditions. Beneath kilometers of ancient ice, in silent darkness untouched by sunlight or seasons, life had carved out its own world, patient, complex, and profoundly unlike anything on the surface. It waited there for ages, hidden but thriving, until the first machines of a curious species arrived to see what the frozen continent had concealed for millions of years. For most of human history, Antarctica was imagined as a barren, frozen wasteland expanse of ancient ice, brutally cold air, and lifeless plains swept by katabatic winds. The continent's surface seemed to confirm that image. It held no forests, no permanent rivers, and almost no exposed rock. But what lay beneath its kilometers-thick ice remained, for many decades, a matter of speculation. The harshness of the environment, combined with the logistical challenge of drilling through ice thicker than the tallest skyscrapers, made direct investigation nearly impossible. That began to change when seismic surveys revealed that Antarctica was not a simple block of frozen land, but a dynamic environment of mountains, valleys, lakes, and rivers. Beneath the ice sheet lay a complex subglacial world, warmed partly by geothermal heat and insulated by the sheer mass of the ice above. Meltwater collected in vast underground reservoirs, forming networks of lakes connected by slow-moving channels. Some of these lakes had been sealed off from the atmosphere for millions of years, isolated from sunlight, wind, and the cycles that shaped life elsewhere on Earth. These revelations energized scientific interest. If liquid water existed beneath the ice, could it host life? And if so, what kind of life could survive in such perpetual darkness, at near-freezing temperatures, under crushing pressure, and with scarce access to nutrients? Theories ranged from microbial extremophiles resembling those found in deep-sea vents to hypothetical organisms living off geochemical energy stored in the bedrock. But indirect evidence was insufficient. The geology could be mapped, the thermal properties could be modeled, the hydrology could be approximated. Yet the biological status of these hidden lakes remained a mystery until the first under-ice Rovers miniature autonomous submersibles designed to withstand the extreme conditions began descending into the darkness. These rovers were engineered with sterile bodies, radiation-hardened electronics, cryogenic insulation, and ultra-sensitive imaging systems capable of detecting faint bioluminescence or microscopic movement. They were lowered through boreholes that sealed behind them to prevent contamination. Once beneath the ice, they navigated using sonar, inertial guidance, and faint magnetic cues from the underlying rocks. Early missions yielded puzzling results. In some lakes, the water appeared chemically inert with almost no organic matter. In others, dissolved gases hinted at ongoing biological processes, but no organisms were immediately visible. Some rovers reported subtle thermal anomalies form pockets in unexpected places, small gradients that could not be explained solely by geothermal heating. The breakthrough came when one rover, deployed into a particularly large and ancient lake, detected faint pulses of suspended particles drifting upward from the lake's sediment. These pulses repeated rhythmically, occurring approximately every 90 minutes. At first they were dismissed as artifacts, perhaps microseismic vibrations, or turbulence induced by the borehole. But subsequent missions revealed that the pulses originated deep within the lake itself, far from any human disturbance. The particles carried unusual chemical signatures. They contained complex organic compounds, including lipids and polymers not typical of microbial byproducts. They also emitted faint bioelectrical signal-steiny fluctuations in conductivity that suggested organized structure rather than random debris. The pulses rose slowly through the water column, dispersed, and then reconstituted themselves near the bottom in a cyclical pattern. These findings challenged assumptions about the lake's biological landscape. If life existed here, it did not behave like known ecosystems. It might not rely on sunlight or oxygen. It might draw energy from chemical reactions with minerals, or from mechanical stresses within the ice, or from processes entirely unknown. Its cycles were too regular to be accidental, hinting at a coordinated system rather than isolated organisms. This prompted a shift in exploration strategy. Rovers were no longer instructed merely to sample fluids and sediments. They were tasked with mapping the structure and behavior of the lake over long durations. They drifted silently through the water, recording patterns in temperature, salinity, chemical composition, and particle movement. With each new mission, the model of the hidden ecosystem grew more elaborate. The Antarctica beneath the ice was no longer a void. It was a vast, cold ocean whose dynamics were governed by pressures and energies foreign to the surface world. And within that ocean, something ancient, persistent, and astonishingly adapted to its claustrophobic, lightless domain. As rovers began to return samples and high-resolution imagery, the first insights into the biology of the subglacial world emerged. They revealed organisms that defied the conventional understanding of what life required. These organisms, if they could be classified within existing categories, did not resemble the extremophiles from volcanic vents or hypersaline lakes. Instead, they displayed attributes that seemed almost paradoxical in combination. Microscopic imaging revealed clusters of filamentous structures embedded in a gel-like matrix that drifted near the lake's bottom. These filaments were hollow, semi-rigid, and interconnected through branching networks. Unlike typical microbial colonies, which form discrete cells or multicellular assemblies, these networks behaved more like distributed systems. Their boundaries were diffuse, their shapes constantly shifted in response to currents and chemical gradients. Chemically, the filaments contained unusual isotopic signatures. Carbon isotopes indicated metabolic pathways unknown in conventional biology, while sulfur and iron isotopes suggested energy extraction from minerals under the lake bed. The organisms also contained trace amounts of rare elements vanadium, tungsten, and molybdenum in ratios that implied they played a structural or catalytic role. Temperature experiments revealed another anomaly. Whereas most life slows down as temperatures drop, the subglacial organisms became more dynamic in the cold. Their internal chemical gradients sharpened, their gel-like matrix expanded, their electrical activity intensified. When warmed, even slightly, the structures lost coherence, dissolving into amorphous clusters. Cold was not just tolerable, it was a stabilizing force. Pressure, too, played a crucial role. Under the crushing weight of the ice, the organisms maintained form and function. But when rover samples were decompressed for surface analysis, many structures collapsed. Only under specialized high-pressure microscopy could their true architecture be preserved. This dependence on pressure suggested that their biochemistry relied on molecular arrangements impossible under less extreme conditions. Another breakthrough came from long-term electrochemical monitoring. Rovers detected faint rhythmic pulsestony electrical oscillations propagating across filament networks. These pulses were analogous to signaling mechanisms in higher organisms, but occurred on vastly slower timescales, with cycles measured in minutes rather than milliseconds. The pulses coordinated the expansion and contraction of gel-like masses, possibly regulating nutrient uptake or waste diffusion. Yet the most astounding discovery was their energy economy. Traditional life depends on redox reaction selectron transfers between molecules derived from food or environmental chemicals. But these organisms exhibited an apparent ability to harvest mechanical energy from microfractures in the ice and chemical energy from rock-water interactions. Even more puzzling, they responded to subtle electromagnetic shifts originating from the ice sheet above, as if their metabolism integrated geophysical signals. This raised a profound question. Were these organisms remnants of an ancient biosphere, preserved in isolation beneath Antarctica's ice? Or were they the product of independent evolution, a second genesis of life on Earth, rooted in geophysical rather than solar energy? Further analysis provided clues, but not answers. Genetic-like polymers were isolated from the gel matrix, but their structure diverged sharply from DNA or RNA. They were more resilient, forming branching networks rather than linear chains, capable of encoding chemical information across spatial patterns rather than sequences. If these polymers represented a hereditary system, they operated by entirely different principles. Rover imaging also recorded the organism's interactions with sediments. They did not burrow or graze. Instead, they grew toward fractures in the rock where mineral-rich fluids seeped upward, enveloping them in soft scaffolds that dissolved once the nutrients were extracted. They lived in slow waves, expanding and retreating with the subglacial tides. This ecosystem challenged every model of biology. It revealed life that did not merely tolerate extremity, but required a life form whose structure, metabolism, and heredity were intertwined with the physical conditions of a world sealed off for millions of years. And where there was one organism, there were many, forming networks across entire lakes and rivers, creating a shadow biosphere beneath the ice. Antarctica's frozen shield had preserved a secret, an ecosystem unlike any other, operating on rules that blurred the boundary between geology and life. We upload new videos every single day, so make sure to subscribe and turn on the notification bell so you never miss what's next. If you enjoyed this video, don't forget to leave a like, it really helps the channel grow. Tell us in the comments what you'd like to see next. Your ideas might be in our next upload. Thank you so much for watching and for being part of our community. Stay tuned, stay curious, and we'll see you in the next video.